Hi everybody. Now that you've got some more experience working with images as 2D arrays, I want to turn to a more serious problem. I'm going to show you how to use an algorithm called the unsupervised k-means clustering algorithm to do blob detection in images. This picture here hopefully illustrates the kind of idea. This type of application would be used a lot in robotics and other types of serious applications. So you'd start with some type of image, possibly from a video. You're going to try and mask objects of interest, but that only creates a two-dimensional array. You actually want to represent those objects as objects, so you want to know where their centers, what points are parts of the object. You might want to know things about their geometry. So then the second step is, given the two-dimensional array of pixel values, how can you cluster them into the natural objects that a human eye could actually see that they form? So the applications of this kind of idea are kind of too numerous to mention, but if you've driven over a bridge in the Bay Area in the last maybe 6 years, you know that there are no longer toll agents. Instead, they take a picture of your car rear end and they localize the license plate. And then once the license plate has been localized, they run optical character recognition to actually pick out what are the actual characters in your license, and they look that up in the DMV database to mail you your bill. If you were going to be running an assembly line for quality control, of course you could hire people to pick over your products, or you could set up a camera that would do the same kind of thing. It would try and mask the foreground objects from the background, and then try and do a recognition task on them. Try and figure out like what's their overall geometry, are there unexpected shapes, are there unexpected colors. So our job here is actually going to proceed in two parts. The first part is going to be just the problem of how do you take a color image and mask the objects that you care about. And then as a second step, we'll turn to how do you take this masked image and actually do the clustering to figure out which pixels go with which blob. Alright, so there's lots of different ways that you can do this step, and the method you want to choose probably depends on constraints about what type of object are you trying to mask and what type of backgrounds are you expecting to see. So I just want to introduce two very basic ideas that cover a lot of they're pretty good for a lot of different kinds of application, and they admit of many variations, so you can add things to make these kind of fancier and more reliable. So the first idea is, well, both ideas are kind of threshold filters. So the idea is you're going to loop through every pixel in your input image, and then you're going to run some test on the pixel. And if the pixel passes the test, then you'll turn it white, otherwise you'll turn it black. So this is, of course, a whole family of techniques, and the big question is what different kinds of tests might you want to run on that pixel? So a really simple one would just be brightness thresholding. So you loop over every pixel and you just test what is its brightness. A quick search on Stack Overflow will quickly yield a solution. So there's actually several different ways of calculating what you might think about as brightness. So there's brightness, there's perceived brightness, and there's luminance. But in all the cases, there's kind of a simple formula where you take the red value, the green value, and the blue value, and you run it through this calculation, and that will give you the brightness, the perceived brightness, or the luminance. If you're interested in what are the differences between those things, or what are other background concepts that you might want to understand, this is actually a pretty good link, Manipulating Colors in .NET Part 1. You don't need to worry about the code aspects of this, but this will cover a lot of different color models and conversions between color spaces. So, as I was saying, you loop over every pixel, you calculate the brightness based on the red, green, and blue values, and if the brightness is above a certain threshold, you'll turn the pixel white, otherwise you'll turn it black. So this can sometimes be useful for highlighting foreground objects in a very kind of rudimentary way. And as you can see here, we've sort of highlighted the foreground objects, but it hasn't done a particularly good job. Another thing to know about this technique is that the results you get critically depend on what brightness threshold value you use. So here in this upper row, I've used a brightness threshold of 100. The brightness in my calculation ranges from 0 to 255. So I'm saying if the brightness of a pixel is more than 100, we'll turn it white. And you can see that fewer pixels are white than the bottom row, where I only tested if the brightness was greater than 30. So in the bottom, I made my threshold lower, and that gave me more pixels that might be considered to be foreground pixels. I called this technique rudimentary, and you might be thinking, well, yes, this is not very good. Like, it produces all of these artifacts here. There's a lot of noise to clean up. It doesn't particularly well separate the objects. That's going to be true of most techniques you try. I mean, I'm pretty much going to say all techniques you try. So what makes this kind of problem exciting and difficult is you're not going to find the magic algorithm that's going to work perfectly for the complete range of cases that you're interested in. So what you need to do is you got to actually use your creative problem solving. You have to think about possibly ways of constraining your inputs. You've got to run not just one algorithm, but potentially several algorithms. So you could run this one, and then you might take this as an input and run it through another filter that would try and find the noise. So it would try and find like isolated white pixels and turn them black, for example. So, like I said, don't be trying to spot what's the perfect algorithm, because no algorithm is going to be perfect. Instead, you want to be thinking kind of what kind of performance is good enough, and how can I create a sequence of techniques that are going to get me there. Okay, let's talk about color masking. So this is another kind of a thresholding filter, but in this case, we're imagining that what we're looking for is a unique color in the image, or almost a unique color in the image. So here, the little tag on the dog says, "I am a therapy dog," and it's yellow. And it doesn't, I mean, just to our naked eye, it doesn't really look like this color. Yellow happens very often in the rest of the image. It happens a little bit in the greens of the grass, but our foreground object is kind of a unique color. So again, what you're going to do is you're going to loop through every pixel in the source image, and then the test you're going to run is you're going to test whether or not that color is close to some target color. And if it's close enough, you'll turn the pixel white, otherwise you'll turn the pixel black. All right, so the question is, how do you test to see whether or not two colors are close to each other? And the answer is we're going to measure their distance from each other in the red, green, blue color space. All right, so let's think about what that means. So, as you know, the way that we're representing color is with the red, green, blue color model. And you can think about the colors as being arranged as points in a three-dimensional space, where instead of an x and a y and a z coordinate, instead there's a red axis and a green axis and a blue axis. So here, if we have a color that's 200 red, 10 green, 5 blue, you can imagine that as a point in space, where you've gone 200 down the red axis, 10 down the green axis, and 5 up the blue axis. So it's sort of in this cube somewhere. And you could imagine a different color, 230, 0, 10. Well, okay, are these two colors similar or different from each other? Well, we're going to try and come up with a measure. We're not going to answer the question yes or no, are they the same or are they different? Instead, we want to compare them and come up with a number, where the larger the number is, the less similar they are. So if two colors were exactly the same and we compared them, it would give us the number 0. So all we're going to do is we're just going to measure their distance from each other in this three-dimensional space using the standard distance function. So the distance function in 2 dimensions you're familiar with. You take the difference in x values, add it to the difference in y values, and take the square root. In 3 dimensions, or even in greater than 3 dimensions, you just take the difference in each of the axes, you square it, and you take the square root of the whole result. So for us, if you have 2 input colors, you take the difference in red values, difference in green values, difference in blue values, you square each of those differences, you take the square root, and that's told you what's the distance between those 2 colors in color space. And now you can do a threshold filter very similar to the brightness filter. You've got a single number that tells you how close is your color to the target color, and you can say if that distance is smaller than a certain amount, we know they must be very close, and so you can turn the pixel white. If the distance is larger than a threshold amount, you'll turn the pixel black because the colors are very dissimilar. So that's how you're going to loop over every pixel, compare it to this color yellow, and then isolate the thing that you care about. Again, there's a lot of features about this simple algorithm that are not very desirable. For example, you have to know exactly what target color you're looking for. And of course, if you have your input image, you can just sample this color using any paint program, and it will tell you what color yellow that is. But in real life, you know, if you took this picture under different lighting conditions, under different weather conditions, even this color yellow is going to have a wide range of possible RGB values that corresponds to it. So again, this color masking technique, pretty rudimentary, but it gives you an idea of what's possible, and you can make more advanced techniques. Okay, I want to mention one more technique that's only useful if you have a video and you're interested in objects that are moving. The video, of course, is a sequence of two-dimensional still images. So what you can do is you can subtract one image from the previous image. So if you have a background, the background, of course, is not changing, and so when you subtract one image from the previous image, you're going to get 0 values, because the 2 pixels will be the same. So when you subtract them, you end up with 0, and that will turn the pixels black. Meanwhile, anything that's moving, you're going to get changes from one frame to the next, and so when you subtract corresponding pixels, you're going to get a non-zero value, and that's going to give you your moving blobs. So that's a really nice technique that you can use for video that's pretty simple and pretty clean. I should note that this really nice video, which kind of looks like it's magically selecting out the people, if you think carefully about what I just said, the output from my algorithm actually shouldn't be giving you these nice highlighted people. I said if we're subtracting successive frames, we're going to subtract the values of corresponding pixels. And so actually you would expect to see differences mostly only along the edges where people are moving. So if you imagine this person moving a little bit, the kind of dark pixel here in the middle is just going to become the dark pixel, you know, a couple pixels over. And so you would actually expect to see pretty dark pixels on the inside of the person. You'd only see bright pixels along the edges where there's a big change between the dark person and the light background. So what is it we're actually seeing here? This is the MOG2 algorithm, which starts from the idea of comparing successive images in a video, but it uses some more advanced techniques, and you can look it up, and it's pretty cool. All right, so your assignment today, I want you to make a color masking filter, and then watch my next video where we'll start talking about the next step, which is the actual blob detection using k-means. And I want you to do some of the preparatory work for your k-means algorithm, which you'll do tomorrow. Good luck!